We want to have a look at inverse functions. To do that though, what we need to do is have an idea of, or remind ourselves of what a function is, and also about continuous functions, because defining an inverse function really relies on knowing what those two things are. So if you remember a definition of function, basically, you can read that one for yourself, but basically what it says, for every x value, there's only one y value. So if we're going to have any situation there, we can't have a situation where we could draw a graph and have more than one y value for any particular x value. Remember our vertical line test. So if we had we'd be able to draw a vertical line, we'd see two y values for the one x value. So that can't happen. So it's a one-to-one relationship between the x and y value. Also, the idea of something's a continuous function. So if something's continuous in a particular domain, so basically it doesn't change, the range of y would be given to us by the function of a to the function of b. So, and thus we could create a value for y there, such that you could g of y, and that would give you back to the x value. Basically saying that as long as it's continuous, it doesn't break up at any point, and it's in that domain, so it doesn't have to be the whole function, but in a particular domain. So you can define that whatever way you like. You're able to get a value of y that there's only one value of x. So that's what it's saying there. So basically we're saying we can go the other way. So if we do what we call a mutually inverse functions, that we can take a function, take its inverse, and then reverse it, it gives us back only the one x value. So that's what it's talking about there. So if we look at our previous example, if we took that one and took the inverse of it, but then went backwards, we'd still get those two values. So we wouldn't be able to get one value there. So we wouldn't turn it into an inverse. We still have to be able to maintain a situation where we've got a one-to-one situation. So you can't have two y values for any x value, or two x values for any y value. So the notation we're going to use is f to the power of -1. Now that is going to be important that we don't mix it up. The inverse function of x is written like this. That's how we'd write an inverse function. That does not mean 1 over the function. That is different. We'd write that in that notation there. So that's really important to realize that those two things are different. 1 over the function of x is the whole function to the power of -1, where we've got the f to the -1 of x is the inverse function. Now you can see that on your calculator, like the tan button with tan to the power of -1, that's your inverse function button. So that's what it means on your calculator. Basically it's reversing the operation. That's what it's trying to do there. So let's have a look at an example here. If x to the power of 3 is a function, domain all real x, its inverse is x to the power of -1/3, domain of all real x. So how do we do that? Well, basically to get an inverse function, it's pretty easy. What we do is we take our function and we swap around the x and y values, and then write that function in terms of y. So we can see that domains and ranges for this one, for both of them, are all real x and all real y. There's no restrictions on x, so there's no restrictions on y for either the function or its inverse function there. There is problems for this one though. If you look at the y is e to the power of x. Now if we swap those around, x and y get swapped around, and then we put y back as our subject, we get y is equal to log of x. Now if we take e to the power of x, our domain there would be all real x. There's no problem putting any value in there. But we know that we have an asymptote at the x-axis for e to the power of x. So y must be greater than 0. So we remember that. Now consider log of x. This time x is going to be restricted. X has to be a positive number. You can't take log of a negative number or 0. And the range is all real y. So it doesn't matter, we can get any value out for y there. So this leads us to think about, well, what can we say about the domains on ranges of inverse functions? hopefully you're thinking the domains and ranges get swapped. And that will happen every time when we take a domain and range of an inverse function. And what the problem's going to be is that can we get situations where we will have to restrict our domains and ranges, or our domains of our functions, to be able to get a function of our inverse function. Not a problem here, but we'll see examples later on where we need to restrict our domain of a function. And the idea would be, for example, a parabola. Parabola is going to give us a problem when we try and take an inverse of it, that we won't naturally get a function. It will be a relation but not a function. So we'll see that later on. But the main thing to take away here is that if you get going for inverse functions or relations, the domains and ranges are going to swap every time for those inverse functions.